Okay, so a standing wave happens when you have two waves of the same frequency, wavelength, and amplitude going in opposite directions and interfering. And so what we'll demonstrate is, two people holding a long spring and then, making it go. And then let's say the middle is going up and down, up, down, up, down, up, down, like that. That would be an example of a standing wave. And so what standing waves have are both nodes and antinodes. A node is a location where there's no displacement, so that would be like here and here. And then you have the antinodes, which you have the largest displacement, which would be right here. So that would be an example of the first harmonic. And an example of the second harmonic, another frequency that this could go at would look something like this, where this is going up and down, this is going up and down, but then in the middle, these aren't moving. So this would be another example of a standing wave. And so there's certain wavelengths that will have standing waves, and the requirements that the ends must be nodes. And then as the wave goes through, you'll have certain spots that are antinodes. And so here's an example of, the first one that we drew here, where we have a node here, and then the antinode in the middle. That would be the first harmonic. The second harmonic, node here, node here, node here, and then the antinodes right here and right here. And then the third harmonic, where you would have node, antinode, node, antinode, node, antinode, node. And in terms of L, if L represents the length of the string, we would have to draw this further out, so it would actually be 2 times L to get the full wavelength. On this one, L is actually equal to the wavelength, and then this one, it's 2/3 of L is equal to the wavelength. And so as you get to higher and higher harmonics, that's going to have a different L as well. Now, when we talk about force vibrations and resonance, it's important to talk about natural frequency first. So if we had these different pendulums, and they're connected here by a rubber band, and we start to move one of these, right? This has the same exact length. So what will happen is this will, go back and forth. It'll push on this spot right here at a certain rate. And as it does that, this is going to push back and forth at a certain rate. And this one is going to start to go with it. Now this one and this one have a different length. So they're not really going to be going to very high amplitudes because their natural frequency doesn't match. And so when we have a natural frequency based on its length, right, if you hit a pendulum and you see it go back and forth, it's going to go back and forth at a certain rate, and that's called its natural frequency. Now, if we end up forcing something at its natural frequency, we call that resonance, where we're pushing something or pulling something at its natural frequency. So let's say the natural frequency of this pendulum was 2 hertz. Went back and forth 2 times a second. If we pushed 2 times a second, the amplitude would get huge. It's like, pushing someone on a swing. If you push someone on a swing at its natural frequency, they're going to go higher. Now what I want you to do is watch different parts of this lecture that will directly correspond to what we were talking about. You can search in YouTube this link here, MIT Professor Walter Lewin's Physics 801 Lecture 31, or type out the link, and then watch these particular parts from 8:12 to 11:30, and then 31:33 to 35, and then 40:26 to 45, and these will be critical for this lesson to give you a visual what's going on.